excuse me. Our next presenter is Tony Leo. Tony is going to be talking to us about FuelCell Energy's carbon capture technology. So over to you.
Hello, everyone. Good morning, good evening, wherever you are. Yes, I'll be talking about how we use, it's a unique approach to carbon capture that actually uses a type of fuel cell that has a lot of carbonate chemistry that goes on that helps us actually concentrate CO2 from an external source. So if you go to the next slide, please. So a little bit about FuelCell Energy. We are in the business of manufacturing and designing and operating fuel cell power plants. So we sell fuel cells to customers. We also do power purchase agreements where we own the fuel cells in our generation business. We service the fuel cells. We do turnkey installation. And we also have a basket of advanced technologies that we're developing for our next generation of products. So, and that's in the lower right there. We talk a little bit about that. There's the use of carbonate fuel cells for carbon capture, work we're doing with ExxonMobil and that we've been doing with DOE. And that's what I'll be focusing on today. We also are developing a product that produces hydrogen in addition to electricity based on the carbonate fuel cell. And we're also doing development work on solid oxide fuel cells, another type of high temperature fuel cell for power generation and things like electrolysis and energy storage. So if you go to the next slide, I'll talk a little bit about what these fuel cells look like before I get into the application for carbon capture, because they're unique, I know, to many people. So on the left there, there's a photograph of a fellow in our Torrington manufacturing facility in Torrington, Connecticut. And he's holding a single carbonate fuel cell package. It's an air electrode, a fuel electrode, and a porous membrane between them that we call the matrix, which is where the carbonate electrolyte is. And there are 400 cells stacked up behind him. So a single stack like that with more or less cells goes into our sub-megawatt products, which range from 250 to 400 kilowatt. And exactly that stack behind him with 400 cells, 4 of those goes into our 4-stack module, which after power conversion and parasitics nets 1.4 megawatt. So in addition to the sub-megawatt, our product line includes a 1-module power plant that is 1.4 megawatts, a 2-module power plant that is 2.8 megawatts. We have a version of that 2.8 megawatt that we use for co-production of hydrogen. And to power that hydrogen equipment, it takes some of the power out. So we go from 2.8 to 2.3 megawatts, but we produce 1,200 kilograms a day of hydrogen. And I'll talk a little bit about how that happens and how it might actually help carbon capture economics. And then at the bottom, we have our 3-module power plant, where the 3rd module runs off leftover fuel from the first 2. So it has a high electrical efficiency, about 60% versus 47% for the other power plants. And that's the biggest system we make. People do projects at larger size by deploying multiples of these systems. The largest power plant, carbonate fuel cell power plant in the world is in the upper right there. That's 21 of those 2.8 megawatt systems in a combined heat and power application just outside of Seoul, South Korea. And the largest one in the US is in the lower right, that's in Bridgeport, Connecticut. That's 5 of the 2.8 megawatt systems, which produce 14 megawatts. And the waste heat from the fuel cells is used in an organic Rankine cycle to make an additional megawatt. So it's 15 megawatts total, and a little bit higher electrical efficiency because of that bottoming cycle that we add. So that's essentially, this is our commercial product line of fuel cell power plants. And what I'd like to do now is talk about how we use a unique aspect of the electrochemistry of the fuel cell to do carbon capture. So if you go to the next slide, please. So there's that guy again holding that cell, and there's a cartoon of what actually goes into the cell. The anode is the fuel electrode. It's where we send methane and steam, basically. The cathode is the air electrode. And the reason we send methane and steam to this hydrogen fuel cell is because it's a high temperature fuel cell. It runs at around 600 degrees Celsius. And that's a temperature, and we have nickel catalyst inside, and that's a temperature where with those catalysts, you can do what we call internal reforming. You actually have a steam methane reforming reaction that produces hydrogen inside the stack from methane. And what that does for us is it's a very efficient way to make hydrogen because it needs heat and it needs water, and the fuel cell produces both of those things. And in taking heat, fuel cell waste heat, to drive the reforming reaction, we increase the efficiency, and we also help cool down and thermally manage the fuel cell stack. So it's a nice feature that has some additional side benefits. So after the internal reforming reaction, we basically have converted the methane to hydrogen. That CO2 that you see on the first line there, that came basically from the methane molecule, that's going to be exhausted. But as we make electricity, as we convert those 4 hydrogens to electricity, you'll see that there's actually 4 extra CO2s that are produced in the fuel electrode. And that's a result of the fact that our carbonate fuel cell, like all fuel cells and like all batteries, all electrochemical systems, work the same way. There's an electrode that makes electrons. There's another electrode that consumes them. You hook a wire between them and you get electricity. But to complete the circuit, there is, you may remember, a salt bridge. There's an electrolyte that transports some kind of ion from one electrode to the other. In our case, it's a carbonate ion. And what that means is that when that fuel reaction happens, you create those 4 CO2s. You need to recycle them back to the air electrode because you'll notice that the cathode reaction consumes air and those 4 CO2s. So what's going to come out of the fuel electrode is the 5 CO2s. 4 of them have to be delivered back to the air electrode, and the 5th is what's going to be exhausted as the CO2 exhaust. And when people started to look at ways to capture carbon from dilute flue gas streams, we realized that this is a potential way that we could use this weird aspect of our technology by interrupting that recycle. If those 5 CO2s come out of there and we grab them, and it's pretty easy to do that because that's a fairly concentrated CO2 stream. The air electrode won't get the CO2s it needs, but we can deliver those CO2s from the external flue gas source. So the idea is that we can send CO2 into the air electrode, and it is essentially electrochemically pumped from that very CO2 dilute stream to a more smaller stream that is very CO2 concentrated. Another benefit of this that we found as we first started to do cell tests and stack tests, and it took us a while to figure out the mechanism, is that if there's NOx in that flue gas stream, about 70% of that NOx will be destroyed as that stream passes through the air electrode channels. And that's a mixture of electrochemical and catalytic processes that do that, but that's a nice benefit of the system. Another benefit of the system is that it actually is a net water producer. So in certain areas, that can be a benefit depending on the type of plant and the water situation in the area. And this fact that we efficiently can convert methane to hydrogen, that's the basis for our hydrogen export product that I mentioned. But it's something that you can do while you're doing carbon capture as well. So it can be an additional revenue stream that can help the economics of carbon capture. So it's converting basically this fuel cell stack into an electrochemical reactor that's doing all sorts of other beneficial things. So the next slide, please. So this basically is the idea. So if you take a fossil emission, and we think this is broadly applicable to coal power plants, natural gas power plants, industrial boilers, steam generators. Most of our development work until recently was funded by the U.S. Department of Energy with a focus on capture from coal-based systems. Coal-based systems, the advantage there is that the CO2 concentration is relatively high. We are, as I'll discuss a little bit more, we're working with ExxonMobil now on capture from natural gas sources, lower CO2 concentrations. So we're working to optimize the capture for those conditions. But in all cases, the basic idea is that you deliver that flue gas to our air intake of the fuel cell. And as it flows through the air electrode channels, the CO2 is electrochemically pumped from the air electrodes to the fuel electrodes. That fuel stream is much less voluminous than the oxygen stream. So you take the concentration of CO2 from 4 to 15% up to about 70%. And now the CO2 is in a stream with a very different molecule. Most of what the rest of the gases in that stream are hydrogen. It's very easy to separate CO2 from that stream. You just compress it and cool it, and it's easy to take the CO2 off from that stream. Now, we are not running the fuel cell on CO2. That would be great, but as far as we can tell, there's no thermodynamically feasible way to do that. The fuel cell is running on natural gas, so there is a natural gas fuel input to the fuel cell. And we cannot do carbon capture unless we make electricity. It's a side reaction of electricity production. And so there is this fact that while you're doing the carbon capture, you're also producing electricity. And that is a significant benefit for the economics. And I'll give you an example of that on the next slide, if we go. So this is a large-scale system that was designed under our DOE supported work, targeting 550 megawatt coal plant. We determined that you would need 319 megawatts of these carbonate fuel cell systems to capture 90% of the CO2 from that plant, and we worked with AECOM to do a fairly detailed estimate of what that cost, capital cost and operating cost, using kind of the rules of the analysis that were specified by DOE and NETL. And we generally express that in terms of overall cost of capture or cost of electricity. But what we're doing in this chart on the right there is we're breaking down the various components of costs and expressing them as the cost of capturing CO2 in dollars per ton. And so you see the raw cost there, obviously capital cost, there's natural gas fuel cost, which you don't usually see in a carbon capture system. And so it all adds up to maybe $70 a ton in that neighborhood. But you have the power generation revenue, which is offsetting it by almost $40 a ton. So you have a net cost of capture, which is where you saw our little dot on that cost curve at the beginning of the webinar. Net cost of capture in the mid-30s because you're able to offset the capital and operating costs of the carbonate fuel cell system with the power generation that you're doing while you're capturing CO2. So that is the main advantage, we think, of this technology, is that power generation revenue can significantly offset the cost of capture. It's obviously dependent on what the local value of electricity is, but with the right set of economics, it can be definitely an attractive proposition. The other thing I'll mention here is that while we're capturing carbon, while we're taking our fuel exhaust and extracting the CO2, there's no reason why we can't also extract hydrogen at that point. And so you can co-produce hydrogen while you're doing carbon capture. And the economics for that varies widely depending on the value of hydrogen, but it's not, you can calculate that there are significant additional revenue offsets associated with that hydrogen production if you find the right customer that can drive the cost of CO2 capture way below $30 a ton if you have the right constellation of hydrogen customers and power offtake. So that is the key advantage of the technology. Co-production of power for sure, possibly hydrogen, reducing the cost of carbon capture. Next slide, please. And I believe this is my last slide. So as I mentioned, we've been working for quite a long time on this technology, going from small cells to the large full-size stack tests. Initially with a focus on capture from coal sources, but as we were doing that work, we started to collaborate with ExxonMobil on capturing from natural gas sources, and we've just expanded what we call this joint development agreement to essentially take our carbonate fuel cell stack and stack module, which is really good at making electricity and kind of good at capturing carbon, and make it really good at capturing carbon. And so this 2-year effort is the first 2 years of an effort that we think we hope will lead to a demonstration of the technology at ExxonMobil facility somewhere. The results that we're getting are bearing out the promise for the technology. So it's early stage, but we think it has the potential to be to play a significant role in carbon capture as we march toward decarbonization.